Okay, well look, thanks to the organisers for asking me along to come and give an update on some of the things that I've been doing with colleagues. Martin's here with me, and I'm really going to take a view which is moving towards, rather than making consciousness front and centre, but moving towards thinking about why do we have internal phenomenal sensations, and what role do they play? I'm going to suggest the role. I'm going to suggest they're not nice to haves or byproducts of the cognitive load, the cognitive processing. But I'm going to try and say, actually, they do something much bigger than that. And actually, they're a very natural consequence of the dynamics, the architecture, all the things that we've heard some about today. The things in the neural columns. There's a terrific architecture there. And the properties of individual neurons, how they work, excitable, refractory, and the properties of the way neurons talk to each other, which actually aren't some, they take time. There are time delays there. For one neuron to talk to another, time delays. And ignorance of that obvious fact leads people making neuromorphic chips to silly errors. And we can do experiments and show that they're silly errors if we want to. So I'll talk a little bit about that. But the massive title there, just reading it. I'm going to explain in the process what a k-dimensional clock is. So let's enjoy this and get through it. I'm aware that there's only me between you and a drink, so we'll get on with it. Okay, well, we know what we've got. We know what the apparatus is. We've all managed to make that functional, and even people from West Oxfordshire, like me, have managed to make this function and make this work. And I can do all of this, and I feel like I do, I have the sensations I have, and I'm doing an immense amount of information processing, not very well, sometimes sloppily, depends if I'm engaging or not. So what's going on inside here? Where does all this come from? So we start to think about that in quite a sort of positive way as to whether we could examine that and come up with physicalist candidates for our inner sensations, and then try to infer their role in the function of the brain. Now, one of the good things about the brain is the sort of fast-thinking advantage, and behaviour economists have obviously sort of like this, but we're going to argue that conscious phenomenal experiences are really they're not consequences of the cognitive. So that's sort of, it's not just because we're doing all this cognitive processing that we then have things as a by. I'm going to argue that they're essential to this, and actually they're preconditioners. So for non-mathematicians, if you solve any sort of inverse problem, it's quite good if you have a bit of preconditioning going on, which roughly puts the system quite close to the answer, and then the math just fiddles it out and fiddles it. So preconditioning is kind of getting you to make decisions from a reduced decision set, for example. Lemma, love is blind. When I'm with my girlfriend, only nice things are going to happen in the next hour. I can rule out a load of things that I don't need to consider. Sometimes I'm wrong, but I can rule out most of the time some of those things. So what's happened is I'm preconditioning my processing, and my processing is really asking questions like, what's going to happen next? What's happening? What's going to happen next? What should I be doing? What do I need to do? Subconscious level. My expectation of what's happening next. And I'm going to argue that these things are really preconditioned. And that immediately tells you that it's about efficiency. So no inner sensations, no preconditions means no fast thinking advantage. Now, we don't meet human beings that don't have a fast thinking advantage because they didn't get boyfriends and girlfriends, and they didn't have babies, so they're not here today. We're the descendant of people who have that, and we all do this fast and slow thinking. We've sort of come to sort of accept that. But actually, it is a real advantage, and it can occur quite naturally if you've got sort of preconditioners. I'd like to sort of talk about Bayesian maths, but we don't have time for that, so let's... Okay, what is a k-dimensional clock? This is easy, right? A one-dimensional clock is a circle. It's called S1. And we call it S1 because it's one-dimensional, and S stands for sphere, so it's a one-dimensional sphere. Normally we think of spheres as S2, don't we, which is a two-dimensional object, curved object that goes the surface of a ball. S1 is just a circle. And TK, a k-dimensional torus, is just a Cartesian product of lots of copies of S1, so S1 plus S1 plus S1. So I've drawn T2 on the top right there, which is a sort of surface of a donut, surface torus, dimensional 2. And I can't obviously draw you a three-dimensional torus. I could if I would, but I can't, because I can't embed it in 3D, so we can't see that. But obviously, just like there is a one-dimensional torus, which is the same as S1 itself, there's a two-dimensional, which is S1 cross S1, which is a circle that way and a circle that way, so that's the surface of a donut. The coordinates would all be phase variables, phi, we call them. So phi 1 through phi k are the k coordinates on this variable, and they're phases. So that means I just identify the mod 2 pi. If I've gone around the clock, I'm back to 12 o'clock or 1 o'clock. So it's just mod 2 pi or mod, whatever you like, let's use 2 pi. And if I have a dynamic on this, they can just wind forwards with a velocity. So phi I winds forward with velocity omega I. And there's no reason why the omegas have to be the same. So I might be going very quickly round that way and very slowly round that way. And then, so it's, you see what I mean. And if k is 10 or something, then I've got a 10-dimensional surface which is embedded in a larger space, but still, conceptually, I've just got these and that's a k-dimensional clock. It's got k phases instead of one phase. And, but everything else is kind of the same. There's quite a lot of work on sort of forcing clocks, and there's 40 years worth of work on forcing one-dimensional clock, and there's almost no work on forcing k-dimensional clocks. But that's what we're going to need. And so when you force it, what people tend to do is to hit it with a sort of zap, hit it with a phase resetting map. And that means that wherever you are on the clock, you're hit with this mighty instantaneous impulse, and it shifts you to some other place on the clock. And the simplest phase resetting map would shift you to a single constant place, regardless of where you started from. But there are obviously more complicated things than that, where the image after the phase resetting depends more critically on the image before, on where you were before the phase resetting. But this, what I'm going to talk about today, this works if we have the simplest kind of really strong phase resetting map that takes everything on the surface, TK, and then shoves it off to some designated phase, and then it starts winding again. And then later on, bam, it gets hit again, and it gets pushed back to this, it's like the Monopoly board where you're sent back to go directly to go. You've got to send back, and then you wind on, and then you hit again. And so that's what's going to be happening here. Who's doing the hitting? Well, we're going to have an array of k-dimensional clocks, and every now and again, one's going to fire in such a way that it hits its partner across the way there. So they're going to be hitting each other. And then they whine, and somebody else hits him, and that's what he resets. So we've got these instantaneous resetting. Of course, in practice, they're not instantaneous. They're just faster dynamics than the winding thing. So mathematicians sometimes call this two-timing. I don't know if we can use those terms anymore, not in the 1970s. Okay, so there's very little work done on phase resetting mappings for high-dimensional clocks, but it should be clear what it is. And so I did a bit of an investigation on mappings from TK to TK and sort of phase resetting. And it's extremely exciting, actually. All of the stuff with Arnold tones, and if any of you know anything about coupled oscillators, a lot of excitement there, a lot of PhD material sort of feel there. Well, we've seen pictures like this from Stuart's excellent talk of the different layers in the cortical column. So cortex, we've all got one, it's corrugated up, isn't it? We saw it earlier. But if we got our iron out and ironed it out flat, it would be, like, it'd be sitting there, would be quite big, wouldn't it? Because we've got it all compacted and squashed down so our heads don't get too big. Even at Oxford, our heads don't get too big. Of course, it would be like a carpet, and sort of orthogonal to the carpet would be these neural columns, and each neural column contains a lot of neurons. And whether all the action's going on in a particular layer, like the yellow layer here, basically the neurons in the columns are very, very tightly connected. And then the column-to-column connections are looser. So this is where the network of networks idea. There's an outer network which is loose connections, and then there's an inner network which is very, very dense. And now we'd like to reverse engineer a human brain, but we can't do that because we haven't got the resolution. There isn't a machine. You know, the strongest scanners will only get us down to, you know, sort of millimeter cubes, and there's lots of neurons in there, so that's no good. What we really want to do is to reverse engineer what's going on in the cortex at right down at the neuronal level, so we can see how information is being passed around in the form of excitation, spikes, and all the rest of it. They thought, well, you know, maybe we could simulate this. Maybe we could actually do it if we had a computer big enough. You know, how do we do? Well, we didn't need all these columns, and each column has 10,000 neurons. And then they'd be arranged in a grid, which is roughly 1,000 by 1,000, so there'd be 1 million. So that's my 10 billion neurons right there. And is it possible to? Yes, it is possible to simulate that. And it's quite exciting when you do that. Neurons themselves have to have some dynamic, whether or not you want to choose your favourite Hodgkin-Huxley or Fitz-Nagumo, or any kind of integrated fire model or anything more exotic. It doesn't really matter. This will work for that. So all that matters really is that the neuron is excitable. That means it has to be sort of zapped by one of the other neurons that sort of sends a message to it, jumps the synapse, comes in at the dendrite and gets into the soma, and then I feel that and I fire. And then it's also refractory in the sense that when I've fired, we then have to wait while the ions re-equilibrate, so I can't fire again immediately. So if I'm zapped a second time, I can't respond to that. I'm just going to, you know, I'm still equilibrating. And then when the thing gets back quite quickly, so that the ions back, then it's ready to go again. So the only thing we need to know about this is excitable. In other words, when it's hit, it will go, if it's hit hard enough. And once it's fired itself, then it has to have a little rest period until it can fire again. And this will work whether you use continuous models like ODEs or discrete models, doesn't matter. Directed delay coupling. Well, if I've got a neuron here and he's going to send something out there and it arrives there, that takes a little bit of time. Not too much time, but it takes a bit of time. And that's a real number, it's not an integer. If it was an integer, well, it sounds mad. Why would it be an integer? Well, multiple of an integer. They'd all be multiples of the same thing. If it was equivalent to integers, then I could sort of just update the whole system on the tick of a clock, which is what IBM's True North chip does. Right. Anyway, we can do this experiment. We can simulate neural columns, and we could have real-time delays between all the neurons. We get quite exotic behaviour, we'll see some in a minute. And then we can make all the delays multiples of a common constant, so we're on the tick of the clock. And what happens is a lot of the dynamical behaviour collapses and quenches. We don't see it. And the reason is that when you get sort of a neuron here and then 2 neurons there and then the 3rd neuron, you know, then the roots take the same amount of time. Whereas if they're different numbers, then he arrives, then he arrives. So maybe this guy hears 2 ticks and he's able to recover and respond twice. So you can see how this would quench the exotic behaviour that we might see. And put like this, it's silly. Let's have real numbers there. It won't cost us anything when we come to the simulation. Okay, here's an example of a little simulation. So there's how many? 8 neurons here, and the adjacency matrix on the top right shows you which neurons speak to which ones, and the arrows show the directions. So, you know, neuron 1 up on the top left there, he goes and talks to number 4, and he also talks to number 3, and so on. And so what we do is we set this up, it's all sitting there, and then we make neuron number 1 fire, so he fires, and then later 4 and 3 fire, and then almost immediately 2 and 5 fire, and then number 3 fires again, and then number 6 fires, and we end up with a pattern, and we form this nice sort of pajama design, design that it's not periodic, it's sort of aperiodic, because this is a k-dimensional clock. And the phases don't need to be in kilter with one another. And I've arranged for those things not to be real, not to be integers, they're real numbers. So actually just, tinkles along like this very, very nicely. And so if you create systems like this and then let them free run, you can sort of analyze them and work out what k is, the number of degrees of freedom. What sort of clock is it? And there are quite a few ways of doing that, and so we tried quite a few different ways, and they generally agree, so that's happy. My favourite is something called state space embedding, but you could probably do something with the fast Fourier transform or whatever, and look and see how many frequencies you've got. You can see why this should be, by the way, because imagine you've got a directed network, very densely connected. Suppose you've got a cycle in that network. And if you just isolated that cycle, it would be possible for a message to go to him, to him, to him, to him, and come back. And as long as he recovered, it would then go around again. And so you've got lots of viable cycles if they're on their own. But because they're refractory, they kind of interfere with one another because they might both get to a same neuron within the refractory period. And so, one cycle might not be viable given that the other cycle's going on. Okay? But because it's so densely connected, there are lots of cycles which are sort of co-viable and can live with one another. Okay? But not all cycles will be able to live with one another. So you can see why you might have lots of cycles. And as soon as you've got a dynamic which is made of a superposition of lots of cycles, you've got a k-dimensional clock. So if we want to abstract this, so the first thing we did was not abstract it. What did we do? We sort of simulated these things, and we made the simple observation that if you increase the size of the cortical column, here I'm doing it for small numbers because this is what my PhD student did. So we go from 5 to 10 to 20 up to 320, doubling each time. And so we're doubling the size of the cortical column, but we're only getting a linear increase there. Right, so it's sort of on a log scale, isn't it? So this explains why we don't meet people with massive cortical columns in the middle of their cortex. Because if you had the space, rather than have one big one, you'd be better to have two small ones. There's a sort of Goldilocks principle. If they're too small, then you've not got enough dynamics in an individual clock. And if they're too large, it's too greedy for energy and space. Okay, you're not getting as much bang for your buck relatively. So it'd be better to have two small columns rather than one large column. And so that's why it's surprisingly uniform when you look across the water. There you go, it's theory, right? So there's some sort of, nature's somehow found a way. And so we don't meet people routinely having very, very large discrepancies in the size of their cortical columns. They all to a similar problem. So here we're measuring K as a function of the size of the column. We can also measure K as a function of other things, like if we make all the time delays integers, and it quenches. You lose lots of behavior. I'm not showing you that. What's a range-dependent network? Right, we've got the carpet, remember, with all these cortical columns on it, and we want cortical columns to be sort of quite related to columns close to them. So some neuron in column 1, ij, will be related to some neuron in column I prime, j prime, with a probability, and that probability depends on the distance between ij and I prime, j prime. So it'll be a monotonically decreasing function of k, which is called the range. These are range-dependent clocks. They have a sort of small world property. What's very good small world property. And I've drawn two that Martin and I used there just for illustrative purposes. So one of them's got, like 100 clocks at the top, and you can see the adjacency matrix. And then I've got 10,000 clocks talking to each other, all set out in a grid, 100 by 100. And there's some randomness there. You can see it's not uniform, the network. So each node now is an inner network, and this is the outer network we're looking at, which is rendering. So roughly speaking, columns talk to neighbouring columns, possibly next neighbouring, but you don't get one talking to one right over the other side. Okay, that's a very low probability method. Don't have to rule it out. That's all a range-dependent network, and that's all we need. So now we've got all the pieces. So we could simulate the whole thing with all the neurons if we had a computer big enough. Or we could say, well, maybe we can't do that. Let's model it. So simulation methodology would be full simulation that have, I should say, 10 to the 9 billion. I should say 10 billion neurons, not neutrons. They're excitable and refractory. You've got network and network architecture, we've seen that. And you've got these type modules and columns, in which case you're going to have 10,000 neurons in each column. It's going to be a lot of work. And we did that. There's a computer in England called Spinnaker, and it has, this has got, twin cores, isn't it? Spinnaker has 1 million cores tied together. Lovely, lovely thing. And so, can I use your computer, please? Yes, you can. Right. And we learned things about spring simulations. We also learned things about the limitations of Spinnaker as well. Hope you're watching, guys, in Manchester. So what did we learn about this? Well, quite interesting things. Because, of course, now we've developed a big data problem because we've got maybe 10 billion neurons all firing, sequences of firing times, and that's quite a lot of data. And so we've developed a heavy lifting problem just to analyse what we just simulated, right? But we could. Or simplify is to say, we've made our own neural columns out of neurons. We've made our own. We've instantiated them not on a binary computer. We've instantiated them in our brains. So maybe we could make something like our own cortical columns out of something, a widget or sellotape and string or something. Maybe someone could develop a thing that actually was a k-dimensional clock and had moments when it could push sparks through the output and had moments when it would receive an input and phase reset, right? There's a sort of specification there. Could we have something that we could make that would receive signals and then phase reset? And they might have different ports for signals because they're going to come from different neighbours. They would phase reset in different ways. And then internally it would have k phases moving at different rates. And if unperturbed, it would just move until it was signal. And then when it got to certain special states, it would send signals out through an output port. So I'm specifying something like a cortical column. Couldn't we build one of those? Well, that's what we do with these clocks, isn't it? We're sort of building one mathematically. But it'd be great if we could find someone who could actually build one, because then we'd have a chance, wouldn't we, of strapping, 1,000 of them together or 1 million of them together and seeing what occurs within. So to simplify, mathematically, I can simulate this with 1 million k-dimensional clocks within a range-dependent network, and I've got to make sure that every clock has these phase resetting mappings. And actually, I can do that on an ordinary PC. Whereas the other thing, I have to go to Manchester and bake time on the biggest computer in the country, right? And the problem, by the way, with using these big computers is that they almost have to create a language where you set up the problems to be run. And this is sort of mysterious because they're allocating cores to jobs kind of thing. And so it's extremely non-trivial getting these things to work. And so you end up, in deep discussion with the team that's supporting the computing facility, which is happening. Okay, so what did we learn? Well, here's some full simulation type stuff. This is kind of one, but we went up to about 1 billion neurons simulating. And what we did was the following thing. We'd pick a neuron as if it was receiving stimuli from, I don't know, your eye or some sensory input. And we'd ping it, and we'd watch what the whole thing did. And then we'd pick another point, and we'd ping. So we weren't allowed to free run. We were forcing it. This is why it's not emergent, by the way, because emergence in maths tends to refer to sort of closed systems which have, or unforced systems which have spontaneous symmetry breaking, and they produce structure from nowhere. Someone came from nothing. But it's a stability problem. But this is an open system. There are inputs and outputs. So there's nothing emergent going on. I'm forcing it, ping, and I'm watching how the whole thing behaves. And I force it somewhere else, ping. Well, I do that a gazillion times, and then for each one of those runs, I get a sort of pattern, which is the response pattern. And then it's quite complicated. I can look and see if the response patterns cluster up. And of course, absolute time doesn't matter. I can shift time because, absolute time isn't important. It's just whether or not I can align one pattern with another. So there's some jiggery-pokery there, which causes a lot of problems in the data science, but nevertheless. And then you end up with a big sort of similarity matrix of experiments. You've done a gazillion experiments, and you say, well, actually, most of these experiments produce very similar outputs. And if you look for them to be hierarchically organised, this is clustering for grown-ups, then you will find them as hierarchically organised. So I'm a little bit cautious about this stuff. But I'm only saying that the response of the system is governed by a number of internal modes. Modes which are dynamic in time, and modes which maybe exist across some or all of the cortex, right? They're sort of competitive to one another. So if one of the modes locks in, it kind of shuts the other out. The response of the system always tends to fall into these classes of modes. And we couldn't have guessed them. Dave Chalmers never told me they were there. He'd never seen them. Because you'd have to do the experiment to see them. You'd have to say, well, he didn't know how he seemed to hit it. He always seems to fall into one of, 150 type of modes or 1,000 type of modes. Like this. And you can arrange them hierarchically, but the trouble is if you look for them to be arranged hierarchically, you'll find they are arranged hierarchically. So it's not very clever. But it gives me great comfort to do so. So just indulge me. So so you could think of the bunches at the bottom as sort of little sensations, and the brain would have the sensation of being in these particular modes. They're firing patterns. They're being forced by stimuli, and they're in that mode. Now, being in that mode would precondition it for whatever comes next, because it's in a mode, and then something else happens. And so, that would precondition the decisions or the inferences it was going to make next, right? If it's able to get into these modes. So, actually, these would be quite important if they were there. To do this, then, you need to have a massive system, maybe 1 billion or 10 billion neurons, and you need to run masses of experiments, which all takes time and money up at Manchester. It's very expensive to do. And it's very exciting to do. So we did all of that and then reported some of these things. And then start to think, well, do I really need to do that? Because for every 10,000 nodes, I know what they're doing. They're a k-dimensional clock. So why don't we just dispense with the neurons and just have the clocks talk to one another? They'll produce the same kind of thing. And that's a bit like asking somebody to make a neural clock out of string and scissors, string and sellotape. Can you do it? Can it have the right? Yeah, so when we do the K-clock simulations, we find very similar things. This is time going down the page for some reason, and I'm going across a load of different phases of clocks. So I've got 50,000, I've got 10,000 clocks, and they've each got 5 phases. So I've got 10,000 clocks in this picture. And the coloration is the phase, which varies periodically between 0 and 2 pi. So to choose a periodic colour wheel in order to, we can do these, and they behave similarly to the full system that we just seen. So we don't need to go to Manchester now and use Spinnaker. We can do this on, on my Macintosh. We can't do this on the Macintosh with 1 million clocks. So we do still need some heavier million clocks. We're doing it with 10,000 here, so a little bit adrift, away from that. This is as big as we can get on a Mac. But you couldn't do this simulation with all these neurons. You'd have 10,000 times 10,000 neurons. This represents. Right, so that's 100 million. Right, you couldn't do that. You can simulate that in a full way. So there's some advantage. But what I'm saying is that having done these experiments, what we're trying to do is to convince ourselves that this is a good model as opposed to doing the full thing. This is a different type of experiment here. So on the left I've got the thing that's free running. There are only 25 clocks here. I've got the thing free running. And then in the middle, what I've done is I'm forcing clock number 12. So it keeps being reset every now and again to 0 by some external. 0 is arbitrary, without loss of generality, it forces it to 0. And so it just gives us that green stripe where they're, right? And on the right, I show the difference between the forced version and the free running clock. So you can see that obviously clock number 12 is different immediately because it keeps getting forced, and then eventually this propagates across the whole cortex. In this case, it's a small cortex. And there's one particular clock out there, you know, number 23 or something. It takes a long time to hear the news, hear the bad news that we're being forced. So, you know, when we fall in love, he's the last to know. This is the sort of thing we'd expect with range-dependent graphs. We'd expect it not to involve necessarily the whole thing. It's more local to where things arrive and moving out from there. But of course, if I now try and enforce it with other types of stimuli, it's preconditioned. Lemma, love is blind. It's preconditioned, and it doesn't have the freedom to just snap to whichever it might prefer. It's preconditioned. So it would make decisions, that's inferences, that's discrimination problems, and all those sorts of things. So, towards a new chip, well, could we instantiate a number of range-coupled k-dimensional clocks within a physical chip? And what would be essential there? Well, most of the things I've talked about would be essential, but if we could get someone to manufacture such a thing, then we could start to glue them together and we could do these experiments. How would we verify such a chip? If someone walked in here with one today, how would they say, well, that's what we want? How would we know? Well, we'd have to check, wouldn't we, that when it was free running, that the different clocks on the chip all had, you know, k degrees of freedom, and they had, you know, maybe random frequencies. We'd have to check, wouldn't we, that when one talked to the other, it phase reset it in a reliable way, and things like that. But there are things we could do, and so Martin and I have thought a little bit about that process. If someone ever came up with one, would we recognise it? And how would we test it? And if you have more exotic phase resettings, that's actually quite difficult. I'll just say that. So we'd have to sort of verify these things. And, but then if we were happy with that, then we could start to group these together, and then we could start to play with it. And this represents a much bigger problem. I suppose what would we build then? How would we use it? So existing digital computation is accurate at logic and arithmetic. It's really good at doing computer things. So I've got a computer, and when I want to fiddle my expenses, I'm using it. Everything adds up. It does logic and it does arithmetic. Okay? And then I say to my computer, you know, do I fancy that woman? And the computer's got, you know, it's got no data, and we have to get loads of data. And, you know, that's going to be hopeless. If I say to my mother, do I fancy that woman? She goes, no, she's not the right sort of woman. She makes up her mind with little or no data, just like that. She's very agile, very competent. Existing digital computer is data hungry and slow at emulating human decisions. Well, most modern AI is emulation. It's not doing brain simulation or anything like that. It is doing things that humans do and sort of trying to kid us it might be doing it in a similar kind of way. But it's not. It's emulation. It's not. It's using power of modern computer to do things that we do and remove grunt work, and that's a very honourable thing. We should thank our lucky stars that we don't have to tag our faces on Facebook. I'll show my age there. Facebook is something that used to exist a long time ago for anyone under 25. Existing digital computation is scalable. You know, if we give it more oomph, it does more stuff. You know, whether we go HPC, parallelized, or whatever. Existing digital computation is useful on well-defined problems which have objectives. So, optimization, converging to, that's why modern ML and DL works. Conscious computation, this is what we're going to build. We're going to build a computer that has internal modes and that can lock in completely one another and can do this sort of thing. That will be highly preconditioned, self-preconditioned, but it will have an internal transient bias all the time. So we have to catch it in the right mood. It's a bit like going to see your boss and ask for a rise. You know, you can pick your moment. It'll be predictably irrational. It will make the same mistakes over and over, just like we do. Same mistakes over and over. But it will have a fast thinking advantage because unlike a zombie, it doesn't have to consider that anything can happen at any time. It's always working within a reduced and constrained decision set, preconditioned by its current internal mode, which are good candidates for phenomenal sensations. It will be all or nothing. in the sense that, we've got what we've got. We can't suddenly scale it up or, give it more oomph. That wouldn't be right, would it? I mean, we don't say, oh, we need a brighter student. Let's get someone with a head as big as a planet. I mean, it's figurative. But we don't really mean it, do we? So actually, we've got what we've got. And I think that, that's a challenge, really, for all of us working in this area. But if someone came in with a widget that could do this, instead of sticking together k-dimensional clocks in mathematics terms, I'd stick together their widgets and see if I could do the same experiment and the same reverse engineering and get the same phenomena out of it. There's very little research on hierarchies of clocks, k-dimensional clocks, all of these things. And even if I'm sort of wrong about 90% of this, I still think there's some key element in here that would benefit a lot of these other theories. Because this is a way of getting dynamics into a situation which is otherwise extremely difficult. So look at the complications of the wiring and wring your hands and decide to go home and read the paper. It's easier. Conscious computing will be agile, making fast decisions with little data. So my dream is that, whether you're a financial trader or a soldier in a warfare situation, maybe you've got a computer that will help you calculate things around you, and something to look at the visible field, spot things over there. But you've also got a computer that's actively giving you advice, like your mother or a conscience sitting on your shoulder, because you really, no, don't do that. Something not right here. What isn't right to know? Something not right. Well, wouldn't that be great? If we had such a computer, one for fiddling our expenses and one for giving us life advice. That would be great. Why don't we all have that computer? So, our roadmap in the immediate future, so much time for a drink. That's a warning against protracted questioning. So how would we harness these simulations? Well, how would we train them? This is something that's sort of bothering us quite a bit. Because we don't want to take the easy route, which is to fall into some of the training and conditioning that, say, is done in ML and DL, AI in general. I think we should look. There's also other type of mistakes. What sort of problems should be addressed? So when IBM produced True North, which is sort of neuromorphic chip, the first thing they did when they built it was sort of write a paper where they'd given it some signals processing to do. Well, we don't do that with a baby or a child. We don't give it some signals processing arithmetic. We get it to recognise a policeman and run away. That's what we do. So I'm joking. So we need to think very carefully about the sort of problems that we would want such a. It's a computational platform, but it's computation not like we know it. It's not going to be accurate logically or accurate arithmetically. It's going to make very agile decisions of very small amounts of data, because it's been there before and it's got this precondition. How could we exploit this in particular applications? What would the applications be? A lot of modern AI actually isn't very good in a live situation. I like to say, DeepMind is always successful where it's literally got a month of Sundays to get the right answer. A month of Sundays is 30 Sundays, 30 weeks, right? It's got to, because we don't mind how long it takes, as long as it gets the right answer. Now we've got a model. But actually, in a transit situation, we want to be able to come up with the answer to what's happening next in a very dynamic and agile way. Right? We don't want things that are going to, if my boss says, well, we're having a meeting at 5 o'clock and we need some data on the table, I can't say, well, this is going to take till a week on Tuesday. We have to trade somehow some accuracy for effectiveness and vice versa. All we've said is that within such systems there are these dynamical modes, which are odd things actually. They sort of compete, they shut each other out, they can be inspired by a collage of inputs. They're quite good candidates for internal sensations. If you put me to it, I'd say they were. I'd say this is when you're in some sort of situation and you feel this, have a sensation you've had before, it's probably a good bet your brain's enjoying the sensation of one of these dances taking place. And you can't spot these dances by taking a photograph. You've got to take a video. Right? It's a bit like showing a picture of a club and asking what music's playing. Unless it's a twist, you can't answer that question. So what other aspects of consciousness might we address if we could build such a thing? I've started to worry about this quite a lot. where would we go with this? Because we're really only at the foothills. I'm saying it seems possible dynamically that we could maybe materially construct these things and then produce a substrate or a platform where we can do these calculations as we do, not instantiated in binary code on a binary computing device, but instantiated in some real thing, like a group of neurons. So it's clearly possible. We've all done it. I think these questions trouble us quite a lot. We often sort of kick this around. And if anyone's got any bright ideas and can help us with this, my appeal to you is that don't hang about, send us an email, let's get together and keep it going, because we might be able to do something where we can synthesize these things mathematically as we can at the moment, and that's a lot cheaper than doing the whole thing. But it'd be interesting to know if we came up with experiments we'd like to perform that we couldn't do on such a platform, in which case we'd probably have to think twice and go and think of something else. So I'm asking you all for a little bit of help with all of this. Right, I declare the bar open. Thank you very much.